Welcome, everyone. So let's take a look at the definition of a sequence. We need these before we start talking about our series and then solving a differential equation using power series solution. An infinite sequence is a function whose domain is the set of all positive integers. So any function takes values from the domain and maps them to codomain, and the y values are forming the range of the function. For example, take a look at a sub n, which is square root of n. This is one sequence. It takes values like n equals to 1, n equals to 2, n equals to 3, and it gives us some output values like square root of 1, square root of 2, square root of 3, and square root of n. So we can just use the general term of a sequence or just list the elements in the range to represent the sequence. Another sequence can be written as Bn, which is -1 to power n plus 1 times 1 over n, which can be represented by its terms. When n is equal to 1, you get 1 back. When n is equal to 2, you get -1/2 back, and so on. For the third sequence, Cn is n minus 1 divided by n can be represented using its terms in the range. When n is equal to 1, you get 0 back, and so on. The last sequence is Dn, which is -1 to power n plus 1. Well, we can list the elements or terms of this sequence, and as you can see, they are oscillating between 1, -1, 1, -1, and so on. When it comes to sequences, we're interested in knowing which one converges, which one diverges. Or basically, as you remember, if you have a function like f of x, you're interested in knowing what's the limit of the function as x goes to infinity. If you have a limit or not. If the limit exists, you say that, hey, the limit exists. Otherwise, you say that the limit doesn't exist. They're basically doing the same thing for sequences. The sequence an converges to number L if for every positive number like epsilon, we can find an integer like n such that at some value, the y values are getting closer and closer to a fixed number like L. If you don't have that L, then you say that, hey, the sequence diverges. We simply say that the limit of an as n goes to infinity is equal to L, or an approaches L, and call L the limit of the sequence. You can visualize this as well. So you can just ignore the finite terms of the sequence if they don't behave the same as we want. But look at the rest of the terms. Here you have this dot here, this dot here, this dot here, and as you can see, it seems like they're getting closer and closer to L. Take a look at this sequence, square root of n. When n is equal to 1, you get square root of 1, which is 1. When n is equal to 2, you get square root of 2, then square root of 3, then square root of 4, and so on. So as n goes to infinity, the limit goes to infinity. So this is an example of divergent sequence. Another divergent sequence is this sequence. The very first term is 1. The second term is located here. So if you look at the behavior, it's look like an increasing line. So as you can see, as n goes to infinity, the y value goes to infinity as well. So that's why it is an example of divergent sequence. The next one is -1 to power n plus 1 times 1 over n. So when n is equal to 1, you get -1 to power 2 times 1 over 1 or 1. So that's why you see a sub 1 equals to 1. When n is equal to 2, you get -1 to power 3 times 1/2 or -1/2. That's why you have this a sub 2 as negative a half, just right here. Another one for you, an is 1 over n. When n is equal to 1, you get 1 back, then n is equal to 2, you get a half, then a third, then a fourth, and so on. So as you can see, if you take the limit of 1 over n, as n goes to infinity, this is equal to 1 over infinity, or just 0. Take a look at this behavior of this sequence here. So the very first term is up here, the second term is here, the third term is here, and then as you can see, as you go to the right-hand side, these terms are getting closer and closer to 0. So the sequence converges to 0. So another example for you is this guy here. Let me erase these. So as you can see, with this sequence, when n is equal to 1, you have this term here. Then n is equal to 2, you have another term. And as you can see, the behavior is like this. They're getting closer and closer to 0. That's why it is convergent to 0. Then we start talking about the infinite series and the n term and the partial sum and convergence and divergence of the sum. If you have just a sequence of numbers, then the expression of the form a sub 1 plus a sub 2 plus a sub 3 plus a sub n plus the rest of the term is basically an infinite series. The number an is the nth term of the series, and the sequence s sub n, which is defined as s1 is a1, s2 is a1 plus a2, s3 is a1 plus a2 plus a3, and finally s sub n, which is a1, a2 plus a3 plus a sub n, which is equal to the summation of a sub k. K starts from 1 and goes to infinity, is called the sequence of partial sums. If the sequence of partial sums converges to a limit like L, we say that the series converges and that the sum is L. We can also write it this way: A1 plus A2 plus A3 plus the rest of the terms plus A sub n, which is represented by the summation of an, and from 1 to infinity is equal to L. That's how you say that, hey, the series is a convergent series. One famous series that you learned is geometric series. If the absolute value of r is less than 1, then the geometric series a plus ar plus ar squared plus ar to n minus 1 converges to a divided by 1 minus r. Otherwise, the series diverges. For example, take a look at this geometric series. You have negative 1 to power n times 5 divided by 4 to the n. You can write this in expanded form. So this is the compact form on the left-hand side, and the expanded form when n is equal to 0, you have negative 1 to power 0, 5 divided by 4 to power 0, which is 5. When n is equal to 1, you get negative 5 over 4, and so on. So if you add these together, since it is an example of a geometric series, and the very first term is 5, and r is equal to negative 1 over 4, it's going to converge to a divided by 1 minus r, or 5 over 1 plus 1/4. Remember that here you have a negative sign, and negative times negative becomes positive, and it becomes 4. So you have a convergent series.